Today we will talk on fluid friction in pipes. So the question is, what is the origin of friction loss? Fluid is consisting of molecules, and these molecules are connected to each other by intermolecular forces. So if this fluid is under dynamic motion, so we need a work to overcome the intermolecular forces, or in other words, to overcome the viscosity of the fluid. The mechanical energy of this work is irreversible. Why? Because it's converted into thermal energy, and it's called energy dissipation, because useful mechanical energy is dissipated into useless thermal energy. This is called friction loss per unit mass of fluid. So EF is the energy loss due to wall drag forces per unit mass of fluid. Okay, EF equal to energy loss due to wall drag force divided by mass of fluid. Okay, we know that energy is equal to force multiplied by distance. So we can modify this equation to EF will equal to force due to wall drag forces times distance divided by mass of fluid. We can overturn distance mass of fluid to be 1 divided by mass divided by distance. So we can say 1 divided by mass divided by volume times area. This will be equal to mass divided by distance. So now 1 divided by rho A, since mass by volume equal to density. Okay, now EF equal to force due to drag times 1 by rho A. Suppose that we have a pipe, this is pipe, and I can say that area, so the force due to the wall drag will equal to stress of wall times area, where area is wall perimeter times length, WP times L. So now EF will equal to wall stress tau times wall perimeter times L length divided by density rho times A area. Okay. So friction loss will equal to tau divided by rho times WP wall perimeter divided by A times L length of the pipe. Since area equal to pi d squared by 4, so we can write the equation to be like this. the multiplicative inverse of WP divided by D square is called hydraulic diameter, DH. So we can write the equation like this. EF will equal to tau divided by rho times 4L divided by DH. So if the pipe is circular, then DH will equal to D, diameter of the pipe. Can we prove this? Yes. Or perimeter, WP will equal to 2 by R in case of circular pipe. This will be equal to by D, then by D divided by D square, we cancel out, and then equal to 1 divided by D. Then we can say EF will equal to 4L divided by D times tau divided by rho. Now the wall stress tau has the same dimensions similar to pressure. So if I want to make this shear stress dimensionless, so I will divide it by dynamic pressure. By this I can get a dimensionless group called F, where F is fanning friction factor, and here tau will equal to F times dynamic pressure. So EF can be written as 4L divided by D times F times dynamic pressure divided by rho. So EF will equal to 4 FL divided by 2 B squared by 2. Let's say this is equation 1. Okay. From Bernoulli equation or energy balance equation, we can write the equation like delta P divided by rho plus G delta Z plus 1 by 2 delta V square plus EF plus W will equal to 0. Okay, this is energy balance equation. So we'll suppose here the 2 points are on the same level, so we can cancel delta Z. Also we'll cancel, we also suppose there is no change in the diameter of the pipe, so delta V square will also be 0 and cancel out. And we also will suppose there is no work to the system, so it's also be 0. So we can write Bernoulli equation by delta P by rho plus EF equals 0. So minus delta P by rho will equal to EF, where delta P equal to P1, P2 minus P1. So in order to cancel the negative signs, we will say P1 minus P2 divided by rho equal to EF. And this is equation number 2. From equation 1 and 2, we can write P1 minus P2 by rho equal to 4FL by D times V squared 2. So this is our equation we will use. So P1 minus P2 will equal to 4FL by 2 times rho V squared by 2. Here's P1 minus P2 is the pressure drop due to the friction. Okay, and we have F here is called fanning friction factor. Also, we have rho v squared by 2 as the pressure, dynamic pressure. Dynamic pressure. We can get fanning friction factor experimentally by drawing the pressure drop due to the friction against dynamic pressure. So the slope will be 4FL by D. And by this I can get fanning friction factor. I can also write this equation in terms of head loss instead of pressure drop. So I can say H1 minus H2 times rho g equal to 4F times L by D times rho V squared by 2. So rho will cancel rho, okay, and here H1 minus H2 will equal to 4 F times L by D V squared 2, and G will transfer to right hand side of the equation, and by drawing the equation head loss against dynamic head, so I can, it's a linear relationship, and I can slope will be 4FL by D. So when any fluid passes through a pipe, there will be two force components act against each other. The first component is due to the inertia of the fluid, or we can say due to the momentum of the fluid, and we can apply here the second law, Newton's second law of motion, force equal to mass times acceleration. The second force component is due to the viscosity of the fluid, and here we can apply also the Newton law of viscosity. Force equal to tau shear stress times area, or equal to viscosity times dv by dl times L square. The inertial forces are destabilizing forces, and they act in the axial direction along the tube, while viscosity forces are stabilizing forces, and they are acting normal to the flow direction or radial to the flow direction. By dividing the two force components, we can get a dimensionless group called Reynolds number. So m times a, mass times acceleration, divided by mu dv by dl times L square. So m here we can use rho v, and a we can use here v by t. And viscosity, we can write it like this. Now we can modify the equation. So L cube and t minus 1. So we can write it like this. This is equal to another velocity and L square. So we can modify or rewrite the equation to be rho v L square v divided by mu v So L will be up and L square will be down. Okay, so it cancel out. Okay, and by this rho VL by mu, L can be, we can use the diameter of the pipe instead. So this will be Reynolds number, and it's equal to rho VD by mu.